So this is going to be the fourth section of the fifth chapter of stats, which is on the mean and standard deviation of a binomial distribution. So you'll see that this is kind of related to something we did a while back. So if you don't remember, we have mean, standard deviation, and variance that we can do for distributions here. And we did those in a video past where we had these formulas for. So to find the mean of a probability distribution, we took all the values times their probability of occurring, and then we added those products together. To get the standard deviation and the variance, we did the following formulas down here. We squared all the values, times them by the probabilities, added them together, and then subtracted that by the mean squared and did stuff like that. Well, the good thing about binomial distributions is because binomial distributions basically have a two-version situation where it's success or failure, instead of doing all these complicated stuffs here, we can get the mean, standard deviation, and variance pretty easily by just doing these short formulas over here. So if we take the number of trials times the chance of success, that is our average number of successes for those number of trials. If we take n times p times q, which remember q is the chance of failure, so if we take the number of trials times the chance of success times the chance of failure, we can get the variance. And then if we square root that, we can get the standard deviation. Remember, variance is the sigma squared, standard deviation is the sigma, and this is the one that we usually want of the two. So we're going to go through some problems here just to show you how easy this is for binomial distributions. And again, our maximum and minimum usual value ranges still apply. So your average plus 2 times the deviation and your average minus 2 times the deviation are what sets up your max and minimum value range. So let me show you kind of how we use these problems or how we use these formulas in work here. So we have 75% of people applying to a college are from affluent families. 350 of them are accepted. If 350 people total, rather, not of them, but if 350 people total are accepted, find the average number and deviation of accepted students that would be from affluent families that we would expect to be. So if the college it's found from past studies accepts 75% of the people from affluent families, if that's the general makeup of it right now, if 350 people apply, on average, how much of those would we expect to be from affluent families? Well, if we have 350 people get accepted, that's n, times the chance of success, which in this case is being from an affluent family, so times 0.75, that will give us our average number of people from affluent families. So again, this is nothing more than a problem we might have had way back when in middle school, whereas 350 people are accepted. We know that 75% of them, generally speaking, are from affluent families. How many are from affluent families? So you just take the number times the percentage, and you get about 262.5, which we'd probably round up to 263, or might even round down, depending on what you're doing this for. But that'd be the general idea. So to get the average value, again, you don't have to take out all the probabilities times all their values and then add them together. It's just number of trials times chance of success, and that's your average value. To get the standard deviation, you basically do almost the same thing, except you square root the number of trials times the chance of success times the chance of failure. And you multiply those through. And that will give you your deviation. So if we do that real quick, let's see here. We take the 350 times 0.75 times 0.25. And we make sure we square root all that. Let me adjust that here. Sorry, can't get my calculator up. There we go. So we take, come on, there we go. 350 times 0.75 times 0.75 times 0.25. So n 350, p 0.75, q 0.25. Multiply together and we get about 8.1. So we'd say that if they accept 350 people, we'd expect that 263 of them, plus or minus 8.1, would be from affluent families. Again, that's not necessarily the best way to describe standard deviation, but for now, that'd probably be the best way to use it there. Now, again, this makes it a lot easier to do than using these formulas over here. We could use these formulas, but it'd be a lot more difficult and a lot more time consuming than just using the simple ones down here. And again, these only work for binomial distributions when you have two designated outcomes. So let's try this again if we accept 1,200 people. So let's say they had a good acceptance rate there, and 1,200 people rather than 350. Well, all that happens is that the n changes. So it'd be 1,200 times 0.75 if it's still a makeup of 75% from affluent families. So this would be no different, except we just trade out the 350 for 1,200. 0.75, 75. We get 900. So we'd expect 900 students to be from affluent families out of that 1,200. And if we want the deviation, so kind of like the plus minus bit, we'd simply take 1,200 times P times Q. Remember, Q is simply 1 minus P. It's the chance of failure. So if we have a 75% chance of success, that means we have a 25% chance of failure, or failure rate, I should say, instead of chance of failure. And so we plug that in here instead of 350, and we end up with 15. So 900, give or take 15 students, would be from affluent families we'd expect. Now, again, we can use this to figure out maximum and minimum usual values. So if I have 1,200 acceptees, would it be unusual if 950 of them were from affluent families? Well, let's check. We know that the average we know would be 900, and the deviation we know is 15. We just got that from the previous example. So it'd be 900 plus 2 times 15, and 900 minus 2 times 15. These would be the upper and lower bounds of my range here. So 900 plus 2 times 15 gives us 930. And then we have 900 minus 2 times 15, and we get 870. So between 870 and 930 are our usual boundaries. 950 is pretty clearly higher than our usual boundaries. So we would say no, it would not, or sorry, yes, it would be unusual, because it says would it be unusual. And this would be yes, it would be unusual. That would be an unusually high amount of acceptees from affluent families out of 1,200. So again, we are using these methods to kind of give us a range of, okay, is there something going on here, or is it just normal random occurrence? Because if you're outside the normal bounds, if you're outside the usual bounds, then that's probably not going to be a normal occurrence. So let's try 2 more here real quick before we go. It's kind of a short video. So we're using a gender selection method. So we have 51 babies are born to couples, and they're trying to have boys. And they use this method here, and it ends up that 39 out of those 51 babies were actually ending up being boys. Because again, that was the goal. The goal was for the couple to have a boy, using this method here to kind of influence the gender. And 39 of them were end up boys. The other ones end up girls. So if the gender selection has no effect, and we're going to assume that boys and girls are equally likely, how much would we expect on average to get from 51 babies? So if we're assuming that if everything's normal, 50% chance of getting a girl, 50% chance of getting a boy, on average, how much of these 51 babies would we, or how many of these 51 babies would we expect to be boys? Well, let's see here. We have our N is 51. Our P is 0.5, because we're assuming the normalcy here. We're assuming that everything's normal. We're assuming the method doesn't work, essentially. So on average, we expect N times P. So 51 times 0.5. So 51 times 0.5. And we get 25.5. Okay, then we also want the deviation as well, which would be good to have. So that's our average. So let's get our deviation as well. So our deviation is root n p q. So let's see what our deviation ends up being. So root of 51 times 0.5 times 0.5 again. We end up getting about 3.57. 3.57 as our deviation. Okay, so this is the average number of boys we would expect from a normal situation, and this would be the deviation. So our goal then here is to figure out, okay, is this an unusually high number of boys? Because if it's an unusually high number of boys, then we probably assume that this is not happening by random chance and that the gender selection method is actually having some effect. So let's see here. An unusual high amount would be 25.5 plus 2 deviations, 0.37 or 0.57. So let's go ahead and see what this comes out to be here. 25.5 plus 2 times 3.57. And we get 32.6, so we'll round that up to about 33. So 32.6 would be up to 33. So 33 would be the maximum number of usual boys we would expect. 39 is pretty clearly higher than that, so 39 is definitely higher than 33. So we would say that yes, this does look to be an unusually high number of boys, and so yes, we would assume that the gender selection method does actually have an impact. Now, it's not 100%, obviously. It doesn't work every single time because only 39 of them out of 51 were boys, not all 51. But we would say that it's high enough that's outside the normal boundaries that we would expect to be if everything was going normally. So we would assume that there is an effect here, that there is something that's changing, and therefore that the method does have an influence. Not 100%, but it does seem to have an influence of making it more likely to conceive a boy than normal. Try one more here. So this is actually a study that was done here. So in a case study, we had 420,095 cell phone users, and we found that 135 of them developed brain cancer. Now, if we assume that this cancer has been studied, and we know that normally people have this much chance, this is the probability, not the percent, but that's the probability of somebody conducting this cancer. So that's about a 0.03% chance of somebody getting this cancer normally. So it's a pretty rare cancer. So this is, again, this value here is based on past studies. We know how rare this cancer is. We know that it's affecting about that much probability of a person getting it. So we want to figure out, okay, are these cell phones causing people to develop this cancer at a higher than normal rate? Okay, so what we do is we assume, again, this is something that we do a lot in stats. We assume that everything's normal, and then we check to see, is everything behaving as it should be if it's normal. If it's not behaving as it should be if it's normal, then we can say, okay, something else is at play here. So notice here in step A, the first thing they say is assume that the cell phones have no effect, which means that the person's chance of getting the cancer is this. Okay? What is the average number and the deviation of people we would assume would get this cancer out of the 420,095 that were using cell phones? Okay, so the average is n, so 420,095, times the chance of success, which in this case is getting the cancer, so 0.00340. And so let's go ahead and do this here. So 420,095 times 0.00340, and we end up with 1,428. So 1,000. Actually, I missed a zero there, didn't I? Yep, there's supposed to be 3 zeros, not 2. Another 0 in there. There we go. So 142.8. So let me put another 0 right in here. So 100, I just forgot my number too. 142.8. 142.8 is our average, and our deviation would be the root of 420,095 times our chance of success, which is this really small number, times our chance of failure, which is simply 1 minus that really small number. 3, 4. I don't know what that is off the top of my head, so I'm just going to write 1 minus that rather than trying to write out the entire thing. I'm going to erase these lines here because they're just annoying enough to me to take that time to do. All right, now I have to write the numbers back in because PowerPoint doesn't like me doing that. So there, there, there. All right, so let's go ahead and figure out what this is here. So we have the square root of 420,095 times 0.000340 times 1 minus 0.000340. Although I really don't need that last 0 if I don't want to, but we'll just do it. So that's about 11.9. 11.95, we'll say, if we round correctly, right? Yeah, 11.95. So let's go ahead and figure out if it's usual or not. So we have 142.8 we would expect. So part B says, is this 135 thing usual or not? So it's going to be plus or minus 11.95. So plus to get the high amount of unusually high, and then minus to get the low amount of unusually low. So let's go ahead and figure out what this would be here. Let me get erasing those lines again. So 142.8 plus, actually it's not going to be that, it's going to be 2 times the deviation. Almost made a mistake there. It's going to be that times 2. So twice the deviation above or below. So 11.95 times 2. And then it's going to be minus that. I'm going to round to the nearest whole number just to make this easier to comprehend here. So 118.9. So 118.9 and 166.7. So 118.9 to 166.7. Right. So those are my boundaries there. So is it unusual to have 135 people out of this group of 420,095? Is it unusual to have 135 of them develop this brain cancer? Well, no, that lies squarely within the bounds there. That is within the bounds of usual values. So we would say that no, it's not unusual. It's not unusually high or unusually low. It's right there in the middle where it should be. So that part C there says, what does this suggest about the publicized concerns that cell phone cause cancer? And again, this was a concern that people have, that these cell phones are causing people cancer because of radio waves and whatnot. Well, by this study at least, that doesn't show any evidence for that. So for part C, I'm not going to write it down here, but for part C, you'd say that okay, well, publicized concern does not seem to have evidence supporting that claim. So you wouldn't say that it's necessarily wrong or right. Again, it's kind of double speak, I know, but your goal here is to convey what the numbers tell you. So you would say the evidence does not support concern that the cell phones are causing cancer. Because could the cell phones be causing this cancer? Yeah, I mean, it's not unusually high, but maybe if they didn't use cell phones, none of these people would have gotten the cancer. We don't know. But we can say that the data as it stands does not support. Sorry, my mic cut out there. We can say that the data as it stands does not support the claim that these cell phones cause cancer. There's simply not enough people getting cancer for it to be unusual, even if they're using these cell phones. So that's the end of this video. Again, the goal here is to make sure, especially you can do a problem just like this essentially. Can you get the average? Can you get the deviation? Can you get the maximum and minimum usual values? And then can you decipher, is a value unusual or is it not? And then if it is or is not unusual, what does that tell you about the overall claim? So again, this problem here is the base example of what we should be able to do once we've gotten this down. So again, if you need to rewatch the video, it's fine. Otherwise, let me know if you have any questions. A little bit shorter than the last few ones I know, so you're lucky for that. I hope you enjoyed the video. Have a good day, night, or afternoon.